Hi friends, welcome to my channel VLSI Gyan. This is Sirisha and in today's session we will see how to implement basic logic gates using a multiplexer. So for that we need to understand the functionality of a multiplexer. Friends, many times it is asked in the interviews in the entry level stage. So let us see how we can implement a gate using a multiplexer. Suppose you have a multiplexer and you want it to work as a gate, then what should you do? So this is what is implementation of gates using multiplexer. We don't have gates, but we want a MUX to work as a gate. So MUX is a very simple combinational circuit, friends, which can be used in any ways. So here, what is a MUX? MUX is like a mini input. It has many number of inputs and a single output line. Many means it has the inputs in the power or multiple of 2. 2 power n inputs. So for 2 power n, how many bits are required to how many combinations will be there? So we have n in select lines. So when 2 power 1 is 2 n is 1, that means it is a 2 power 1 is 2. So it is a 2:1 MUX. So basically in a MUX, we have n select lines and 2 power n input lines and the single output line. So friends, let us see the operation of a single, 2:1 MUX. So for this, you can see in the figure, it has two inputs, I0 and I1 and a select line. Because two inputs are there to select this, we have a single select line. Now, what the MUX is doing that when the select line is 0, that time it simply selects the input I0. So whatever the data is present at this input line will be carried towards the output. And whenever the select line is 1, that time it selects the input 1, and whenever the select line is 1, it passes whatever the data is present at input 1 to the output. This is what you can see in the truth table. Where S is 0, Y is I0. When S is 1, Y is I1. So using this functionality of the MUX, we need to implement all the gates. So let us start with the basic gate, that is our AND gate. So AND gate is a gate where when you have the all the inputs as 1, then only you will get the output as 1. Friends, you all know the symbol of AND gates. Here I have shown a 2 input AND gate. So it has two inputs, input A, input B, and a single output. And the output is generated based on this truth table. A and B means both has to be 1, then only your output is 1. So you can see when A is 0, B is 0, output is 0. A is 0, B 1, still only single input is 1, so output is 0. A1, B0, 0. 1, 1. So this AND gate we need to implement using a MUX. So there is a very simple method which you can follow. See friends, we have a select line and we have here the two inputs and the output Y, which is for the output of MUX. But here what you want that this should work as a AND gate. So for that what you can do is the select line which is here, that you can consider as any one of the input. So for simplicity you can see that these are the combination of inputs. You can take any one, but for simplicity this is the best. Okay, so for A is 0 means you can consider A as select line. So you can say that when select line is 0, what happens to the output? Output is always remaining at 0. Irrespective of the value of B, the output remains at 0. Correct? And when A is 1, that is select is 1, that time what happens? Whatever you apply at B, that is there at the output, right? So this is how we are going to implement. So what we have done here, when A we are considering as the our select line. So I will tie my A to select line. Now this is my select line. Now when A is 0, that time my output is always remaining 0. We know that when A or the select line is 0, it will consider I0 and it will pass that value to the Y. So what is the value? Always remains 0 irrespective of the other input, it is always remaining 0. So have to put 0 over here. Next, when A is 1, means my select line is 1, that time we know that I1 will be selected. So what value we should put at I1 is nothing but the same as B. So I will write here B. So to implement an AND gate using a 2:1 MUX, one of the input should be connected to 0 and the other input should be 1, and you have your select line as your one of the, right? So select line is nothing but A here, and one of the input is tied to 0 and the other one is B. This is how we implement a AND gate. Similarly, we can implement all other gates. Let us see how we can implement the other gates. Next comes the OR gate. For an OR gate, we know that if any of the input is 1, then the output is 1. Right? So here, this is the symbol for the OR gate, and we can see that this is the truth table. A is 0, B is 0. When both the inputs are 0, output is 0. When A is 0, 1 is 0. This condition is true for OR gate because it requires only one of the input to be 1. So it is 1. And when A is 1, B is 0, here also it is satisfying the condition. Then here the output is 1. When both the inputs are 1, the output is also 1 over here. Now again the same procedure we will follow to implement using a 2:1 MUX. So consider these as the select lines. When select line is 0, what happens? What you get? Compare the output with the other input. So you get the same value as your output. So simply I can write here, this is my A, right? And what I'm getting at this input, when A is 0, we know that when A is 0, what will happen? It will select the input line I0. And what is I0? It is same as B. So I am getting here B. Similarly, when A is 1, what output we are getting? We are getting 1, irrespective of the value of B. Whether B is 0 or 1, we are getting 1 only. So when A equal to 1, what we are getting? We are getting 1 here. So this is how we can implement a OR gate using 2:1 MUX. One of the input is B and other input is 1. Then we can implement a OR gate using 2:1. Similarly, friends, we will implement all other gates. So now I want from your side. So please put the video on pause and try to write the implementation for, sorry, this is again the OR gate for NOT gate. NOT gate is very simple. So I want all of you to write the implementation of 2:1 MUX using NOR gate. So friends, we can see that for a NOR gate, sorry, NOT gate, we have the input as 0, then we'll get the output as 1. And when we have the input as 1, we get the output as 0. So here the same thing we need to implement now using a 2:1 MUX. So what we can do, simply here single inputs are there. So I will take here as this is suppose my input. Okay. A or any letter because only single input is there, right? So when A is 0, what will happen? The output is always 1. So I'll simply connect here 1. And when A is 1, the output is to be 0. So I will give 0. So that will pass to the output and I will get that value, right? So when A is 0, the output is 1. And when A is 1, the output is 0. So this is how we can implement a NOT gate using 2:1 MUX. The next gate is NOR gate. NOR gate is a very important gate because it is a universal gate. So we know the symbol. It is a OR and a not connected bubble at the output side. It is nothing but NOR gate. And let us come to the truth table of NOR gate. So when A and B both are zeros, then for an OR gate it is 1. So the NOR gate is a complement of that. So it is 1. For a OR gate, it is 0, right? When both the inputs are 0, it is 0 for OR gate, and here it is 1. Similarly, when for both the inputs are, if one of the input is 0 and the other one is 1, then here you will get the output as 0. Here also 0 and 0. So this is how the truth table of NOR gate is. Let us now implement this using the 2:1 MUX. Similarly, friends, we need to consider the same procedure. A equal to 0, A equal to 1. So A, I will put it here, and let us see what is the output value when A is 0. See, when A is 0, B is 0, output is 1. B1, output is 0. So when you compare this, what you will observe is whatever the value of B is there, that is complemented here when A is 0, right? When A is 0, if B is 0, it becomes 1. If B is 1, the output becomes 0. So we can simply say that it is a complement. So I will take B bar or B dash, complement of B, as one of the inputs when A is 0. When A is 1, what happens is, when you compare these two, you can see that it is 0 only. Whatever the value of the B is there, irrespective of B's value, it remains 0. So this is how you can implement using 2:1 MUX. I think it is very simple and easy to understand, and many times it is asked in the interview questions in entry level for RTL design engineer or as well as the DV engineer. So you must be familiar with this kind of implementation. So next let us go to the another gate, that is NAND gate. Friends, similar operation and similar procedure we can use here. This is your NAND gate. NAND gate is nothing but AND and a NOT gate. So you can see that the truth table, when both the inputs are 0, output is 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Similar procedure to implement. What you need to do? You need to consider when A is 0. These are the conditions, two conditions when both the A values are 0. Here also it is 0, here also it is 0. So when A is 0, what happens to your output? Your output is 1. If it is B is 0 also, it is 1. B is 1 also, it is 1. Means it does not depend upon the value of B. It only depends upon when A is 0, it is simply 1. So what you can do is, for the implementation, you can take this A as your select line, and you can consider the output in line as 1. Sorry, the input line as 1. You can connect I0 to 1. Now for the other condition, when A is 1, check what happens to your output. The output is 1, the output is 0. So what is happening here? We'll try to relate the output in terms of B. So when B is 0, the output is 1. When B is 1, the output is 0. Means what is happening here? It is complemented. B is complemented. So when A is 1, we get the output as B bar. So that is what we have done here. Simply, friends, once again, I will explain in this figure. See, when A equal to 0, means the multiplexer will be selecting the I0 input. So what is your output now? 1. Whether it is right or not, let us check. Yes, it is right here. We can see when A is 0, output is 1. When A equal to 1, let us see what happens. Now, your multiplexer will be selecting this I1. So now the I1 is going to the output. What is I1 now? I1 is B's complement. So whatever the value of B is there, it will be complemented and that will be your output, right? So if B is 0, so you will get it output as 1. If B is 1, you will get the output as 0. So this is, we have implemented NAND gate using a MUX. Now let us go to the other gates. The next gate comes is our XOR gate. This is the symbol for the XOR gate and this is the truth table. When both the inputs are 0, its output is 0. When 0, 1, it is 1. 1, 0, it is 1. And for 1, 1, it is again 0. So it is also a very simple gate which you can implement using a 2:1 MUX. Friends, you can use these gates. You can implement using a single MUX or you can use using 2 MUX or more number of MUXes. So it depends upon you how you want to do. Here I am using a single 2:1 MUX only. So when the A is 0, we can combine these two input combination. When A is 0, we need to compare the output in terms of the other input. So comparing the output. So when A is 0, if B is 0, output is 0. If B is 1, output is 1. That means when A is 0, the output is same as B. So I will take I naught as B because when A is 0 or select line is 0, the multiplexer will be selecting the first input I naught and I naught is nothing but the line which is passing to the output at that point. So what is my output at this stage when A is 0? It is same as B. So I have taken B. So whatever the value of B will be there, that will be my output. Similarly, when A is 1, that time we need to compare the output with the other input remaining. So here you can see when A is 1, B is 0 and output is 1. B is 1, output is 0. So we can say that the output is complemented. Here you have complemented output, right? B is nothing but the complement of other input. And here it is the same. So this is what we are going to implement in our multiplexer. So this is my XOR gate. When A is 0, it is B. When A is 1, it is B bar. Similarly, friends, we have one more gate remaining. That is nothing but our XNor gate. So let us implement that also using 2:1 MUX. So this is our XNor gate, exclusive NOR gate. We have two inputs and a single output. Here we have considered a two input exclusive NOR gate. Okay. So the truth table is when A is 0, B is 0, output is 1, 0, 1, 0, 1, 0, 0, 1, 1, 1. Friends, I'll tell you a simple trick to remember the output truth table of this gate. See here that for XNOR gate, you want always the number of ones to be an odd, including the output. So here you can see when both the inputs are 0, so there is no 1. So we have to simply consider the output as 1. Here 1, 1 is there, so no need to have add or the output is 0. Here again it is 0. Here you have two ones, but we want the output to be a odd one. So we are adding 1. So this is a simple trick actually to remember the truth table. This is the equivalent circuit. You have a XOR gate and you have connected it to the NOT. So it becomes your XNOR gate. Now coming to the implementation of XNOR gate using a 2:1 MUX. Similar procedure, friends. Let us consider A equal to 0. When A equal to 0, compare the output in terms with the other input remaining. So when A is 0, what is the value of B? B is 0 here. And what we are getting? 1. When B is 1, we are getting 0. So we can simply say that when A is 0, it is nothing but B's complement because B value is complemented. If it is 0, it becomes 1. If it is 1, it becomes 0, right? Now, the next condition, when A equal to 1. When A equal to 1, friends, compare the output with the input. Other input remaining. What is the other input remaining? B. So output is 0 and B is also 0. Input B is 0, output is 0. Input B is 1, output is 1. So you can simply say that it is now B. Coming to the multiplexer, select line is A now. When A is 0, what will happen? It will select the I naught and our I naught value has to be B bar. then your output will be B bar. When A is 1, it is B. So this is, friends, how we implement the basic gates using a MUX. This is a very important topic. So I hope it is clear now and you can implement any gate using the MUX. Please subscribe to my channel, like and share, because it gives motivation to make new videos. And thank you very much for watching this video. Thanks.